Neat, a few of these accepted proposals were the topic of my master's thesis a couple years ago. Exciting to see a major release, though admittedly it seems a little arbitrary if there aren't any breaking changes, and very problematic if there are. WA will likely never publish anything backwards and compatible. This is the web after all. If WA's worst versioning sin is abusing the major version to collect a number of currently implemented proposals under a canonical name, I'll live and pray that nobody from the USB or HDMI standards committees get anywhere near. Well, backwards compatibility is really a spectrum, and the interpretation of the concept can fall at either end of the spectrum, depending on what a person is working on. As far as WASM is concerned, there are at least two known discrepancies that made into this draft as documented here. Especially the last comment by Alex here seems interesting to me. On one hand, the observable result of the execution changes for the same program. On another, who is going to bother writing such programs? Should WebAssembly specification be allowed to assume nobody does and make changes such as these? As somebody familiar with WebAssembly, how would you do FFI? Like say you wanted to make a J2534 DLL. How would you export these DLL functions or even call functions from other DLLs, dlopen/dlsym, etc.? You can import host functions and data to a WASM VM much like you would with, say, an embedded Python VM. The exact API depends on which VM implementation and host language you're using. dlopen/dlsym support is still in the works, for example, C0. You can't call function pointers directly from WASM, naturally, but it is possible to wrap dlsym so you can use it from a WASM program. There just isn't a standardized/pre-made way to do it yet, so you'd have to write the glue code yourself. Edit, the Mscripton WASM toolchain seems to support dlopen/dlsym, C0. You may want to look into WASM interface types, which is defining what amounts to an IDL for WASM so that different languages have common calling conventions. I don't know if there's a better intro article. I believe this is the current iteration of the proposal. I assume this page describes what changed since 1.0, since the original release 1.0 of the WebAssembly specification. A number of proposals for extensions have been integrated. The following sections provide an overview of what has changed. Thanks. Here's a quick summary from there, with links to the implemented proposals. Multiple values, generalized the result type of blocks and functions to allow for multiple values. In addition, introduced the ability to have block parameters. Reference types, added and as new value types and respective instructions table instructions. Added instructions to directly access and modify tables multiple tables. Added the ability to use multiple tables per module bulk memory and table instructions. Added instructions that modify ranges of memory or table entries. Vector instructions. Added vector type and instructions that manipulate multiple numeric values in parallel, also known as SIMD, single instruction multiple data. Sign extension instructions, added new numeric instructions for performing sign extension within integer representations. Non-trapping float-to-int conversions, added new conversion instructions that avoid trapping when converting a floating point number to an integer. Appreciate this. Can you explain why there appear to be English-looking letters used for terms but with alternate Unicode versions? Makes everything look jumbly, but I'm sure there's a good reason. Are you talking about the MathJax rendering used for instruction names? False alarm. I think it's a font rendering problem on Safari. When I tried Chrome and Firefox it didn't appear. For example, under external types you see this grammar rule, extern type, =, func type table type, mem type, global type. On Safari, the tokens fun, table, men, and global render with weird font baselines on some letters, C, O, E and are raised a few points higher than they should be. I just figured these were odd substitutions for ASCII characters from further in the Unicode alphabet. Maybe to avoid collisions with other reserved token names or something, vamping here because it was all I could think of. Sorry about that. So it looks like it's basically slapping a 2.0 on standardized features from the roadmap. I think that's the process, yes. Features get proposed, discussed, implemented, then eventually when they're done they're moved into the spec and tagged with a version. The additions that look interesting to me are multiple return values for functions and table manipulations. IIRC tables are used to communicate things like function pointers with the host executor, maybe like of table but more general. No garbage collection integration yet? Or is it done as a separate work? It looks like garbage collection is at the proposal stage, one step before it would start to be implemented. During this phase, one or more implementations proceed on prototyping the feature to the point that a comprehensive set of tests can be added. A test suite is added. These tests need not pass the reference interpreter at this point, but should pass on some implementation. Here's the proposal. And you can see it's being actively worked on. Under implementation in Chromium 2. And Dart has an experimental WASM backend that leverages that work in V8 here. Is garbage collection really needed? Only way to get rid of JS as an intermediary for DOM access, yes. GC and the DOM are intimately related. Direct DOM access could already be implemented with reference types. GC integration is not necessary for that. What is blocking it from being implemented in browsers at the moment? No, but it helps. Opens up the target to an additional subset of devs. Isn't it part of the runtime? It's for proper integration of garbage collected languages, otherwise you need to embed your GC too, which bloats the WASM. JS host VMs have very good GCs these days, so hooking into them allows for better integration by e.g. Go, Java, C#, etc. Right now WASM is really designed for C/C++/Rust. Also, WebAssembly can't support most GC runtimes now, because you can't scan the stack for roots. You can keep your own shadow stack on the heap, but that has a bunch of pretty bad performance implications. This actually impacts C/C++/Rust codegen as well, since they can't create references/pointers to anything on the stack, and have to build their own shadow stack. I think this is done in Binarian or LLVM itself. I understand it's a security thing to disallow direct stack access, but most languages and runtimes expect it. Anyways, that's why there needs to be support in WebAssembly for GC, because there needs to be a safe way to walk the stack, aside from the obvious JS interop considerations. JS host VMs have very good GCs these days. Aren't all of them single-threaded, though? That is, they only work in a VM with a single thread which the GC shares? Since WASM is supposedly finally bringing real multi-threading to the web, how would that work? It seems like you'd need a new GC for WASM rather than just repurposing the JS GC. Many JS GCs are internally multi-threaded and can handle multiple allocators. Even though JS isn't itself multi-threaded, the JIT and runtime systems now are, and they can concurrently allocate onto the heap. V8 has had to move towards this ability very gradually because of assumptions from the single-threaded world, but it's much more likely to support multi-threaded WASM GC, should it be necessary, in the future. Is bringing your own GC that hard? I think putting one in the spec would bloat WASM runtimes, which would be more concerning. I've done it for Virgil. It's a major pain, because WASM, by design, does not give access to the value stack. So to find roots you need to spill them into memory into what is called a shadow stack. The problem with bringing your own GC isn't just that, though. It's that using linear memory for everything, you're forced to put external references in a table, which roots them. Tables aren't weak, and even if they were, it's possible to set up a cycle between the linear memory GC references and external references so that leaks happen. This was a problem in other contexts, for example, in V8 embedded into Chromium, and the ultimate result is that you need cooperative garbage collection across two heaps, with queues. While V8 and Chromium trust each other, both not to screw up, and to be fast, it's hard to see how to make that cooperative garbage collection contract work with untrusted WASM code. Go ships its own GC as part of the binary for non-WASM targets. Why should WASM be special? Is WebAssembly faster than JavaScript? Any good benchmarks you can link me to? I found one of Daniel Lemire's, 0, from 2018 which seems to suggest it's basically not much faster. 2018 is long enough away from now though that this post may not be relevant. I don't know. It's odd to me how WebAssembly seemed to be started as a way to get performance improvements by working with cached instructions, and maybe also explicit memory management and integer types, but I don't hear much about performance these days. Maybe I'm not paying attention. Instead, I hear more about it as a universal platform or a way you can run C/C++ code in the browser, like TreeSitter and CPython and Ruby, etc. Or about people using it in edge compute or as the engine for smart contracts. In those ways you could just as well have used the JVM though. 0. The big thing that makes JavaScript slow, that the optimizer can't really fix, is complex data structures. For example, if you want to implement an editable string, you have to do so using an array of smaller strings and hope the optimizer can figure it out, or slice, and rejoin a single, immutable string. Either way, your JavaScript code will be slower than the C/Rust equivalent because the language is less expressive. JavaScript has the same problem with B-trees, skip lists, ropes, gap buffers, AABB trees, and so on. You can implement all of this stuff in JavaScript, you just end up with much more memory indirection than you want. And for trees with different internal nodes and leaves, your code will give the optimizer indigestion. In my experience, basically any of these data structures will run about 10-200x slower than their native counterparts, if both are well optimized. To me this is the big performance advantage WASM has, that we can make high-performance data structures. I'm working on a CRDT in Rust. The fastest JS implementation I know of takes about 1 second to replay an editing trace from a user. In Rust I can replay the same trace in 0.01 seconds, 100x faster, by using a skip list. What are your thoughts on the JavaScript YJS CRDT implementation? I'm admittedly pretty new to the space, so I don't know much about performance comparisons. Haven't noticed any significant performance problems with it, using it for collaborative editing on 100,000 Word documents, but would love hearing what you think. It's fine. I think it's the best CRDT out there right now, but Kevin had a few years head start on me. I haven't done a lot with YJS personally. And I don't agree with a few of Kevin Johns' design decisions, but none of them are deal breakers. The way deleted data is encoded in YJS is awkward. Versions store a list of which content has been deleted. So versions are bigger than they need to be, and you can't replay the editing history without stored snapshots. I think the knowledge of which elements have been deleted should just be saved into the binary format alongside the inserts. For JavaScript objects, YJS pretends each value is actually a list, with everything after the first element ignored, so it can reuse the logic for list editing. This is overcomplicated compared to Shelf or something like it. YJS's internal structure is a linked list with cached offsets. This works okay, in practice, because inserts usually appear close to each other, but it means YJS has O(n) squared, performance to process n edits rather than O(n) log n. Diamond types as via WASM is about 30x faster as a result, though as you say, YJS is still plenty fast enough in practice for most applications. And this gap will narrow once YRS is working well. YJS can have an interleaving problem when concurrent items are prep-ended at the same location in a list. The current, new, diamond types file format stores the origin position plus parent's information instead of storing left origin/right origin fields. This lets DT have a smaller file size while storing more information than YJS stores. And I think this format is easier for applications to encode and work with, and it will make pruning easier when we get to it. We should also be able to load and save faster than YJS, but I'm not benchmarking that yet. But all of this stuff is pretty minor. YJS works well in practice, and it's quite mature. Performance will only get better with the YRS Rust implementation. For diamond types, I had the benefit of being able to copy some fantastic implementation ideas from YJS. If diamond types is better than YJS, it's because I'm standing on its shoulders. Adding to this great comment with my own experience at work where we extensively use signal processing and time series compression algorithms to visualize large amounts of biological signals in the browser. WebAssembly is less than 10% to 20% slower than native code in our benchmarks and tests for algorithms, like fast wavelet transform and bit packing. WA allows us to aggressively optimize ahead of time when compiling, and be less sensitive to JS engine performance pitfalls around JIT optimization and garbage collection. Throwing in my data, for physics simulation code, WASM versus native was identical, provided the native code was compiled with automatic SAMD optimizations disabled. On the one hand, that speaks well of the idea of WebAssembly, on the other, disabling SAMD is highly artificial. It's good to see basic SAMD being made standard, though the 256-bit wide SAMD instructions are still being finalized, and those will be necessary to really have a chance at evening out performance versus native. I think Lemire's measurements are unacceptably lazy. WebAssembly is faster than JavaScript on the right things, there are many measurements showing this. Typically, measurements that show JS on par or beating WASM either end up falling into micro-benchmarking traps, one small, hot loop, something gets dead code eliminated, or they end up relying on a particular type of dynamic optimization that WASM engines don't yet do, inlining, escape analysis. With SIMD and threads, WASM can absolutely crush JS performance. Why would WASM engines need to do inlining and dead code elimination? My impression was that WASM is basically native level code, save for register allocation, and some Arch-specific peephole optimizations. Dead code elimination is the job of the C++ compiler. Generally, I don't disagree, but not all producers are LLVM. And JS inlining is driven by dynamic heuristics, speculatively inlining likely candidates, whereas statically compiled C++ code generally doesn't have speculative inlining. So a WASM call _ indirect will not get dynamically optimized into a guarded inline. Isn't SIMD new in this release of the spec? How can WASM crush JS using SIMD if they only just added support? It's been implemented in browsers for longer than the spec has been out. In fact, one condition of a proposal being merged into the spec is that 2 production engines must have implemented it. I don't care if it's faster, the same or even slightly slower. The sooner I can start working on large applications with a strongly typed language that isn't just transpiled to JS, the better. My point is that compilation targets are somewhat arbitrary. Non-JavaScript languages have been compiling to JavaScript for a long time. What difference does it make for you as a user of a language that it compiles to WebAssembly than to JavaScript or any other VM? JavaScript being garbage collected, having a rather complex runtime, not having proper integers etc. makes it a rather unfortunate compile target. Yes, you can do it and it is done, but JS idiosyncrasies leak into the source longs pretty easily. That's a good argument, but more of a maintainer argument than a user argument. From a user it should be transparent except for performance and FFIs. Well, the user perspective is, suddenly there are compilers for all kind of languages targeting the browser because WASM makes it easier for the maintainers to build them. Sure, you could have implemented unsigned integer semantics on top of bool arrays in JavaScript years ago, but if the result is too slow you have gained because the compiled C++ code does not run fast enough to be usable. Regarding numbers, JavaScript supports bytejns now, which makes the situation a little bit better. But maybe a lot more complex. I wish they were somehow better supported by JSON.parse though. Compile to JS is a leaky abstraction that gets messy when JavaScript's type system and built-ins collide with your languages. Some languages also need specialized tooling for their compile to JS stuff, rather than treating it as just another compile target. I usually find it causes more problems than it solves, but I'm hopeful that someday WebAssembly can make compile for web transparent enough that non-JS languages really feel like a great experience in the browser. You could use Dart, I guess. Flutter is similar to WASM apps like Figma in that they manipulate a canvas, not the DOM directly. I'd assume most WASM apps in the future will look more like that than true DOM manipulation. There are others however, such as you written in Rust, or Blazor in C#. Interestingly enough, Dart is also pretty deep into adding WASM as a compile target to act as an alternative to the current compile to optimized JS approach they do currently in the browser. You are right though, they are going to be the first big WASM/Canvas and Web GPU framework, as opposed to the generations of JS/DOM. It will be interesting to see where they land with it. I'm quietly hopeful, especially once you get AOM sorted in the browser too. I think the real test is going to be when they decide to migrate over the multiple $1 billion of revenue project that Google Ads is from JS-based Dart to WASM intended to eventually make it into the main spec, or do they remain standalone? But not much to look at now, just source GC, and no docs, threads, atomics, component model, interface types. I do see some improvements. I'm not sure what to expect to eventually make it into the spec, and what will continue WebAssembly version is quite a bit faster. Personally feels like it marks the start of WebAssembly's first full era. This post, discussed on HN recently, goes into some of it and provides some further links. And only then can we really understand and explore what WebAssembly means to the world. Rust got an early start with WasmBindgen, doing all the lifting on their side, but it's not reasonable and only semi-interoperable, having each language rebuild that Bindgen system and Abinger itself, hence canonical ABI and component model. Edit, Tux3 has a good comment linking the changelog, noting that indeed number of specs have been integrated. Really excited for multiple table per module support. The idea of a capabilities-based sort of system, where a module is handed a couple working sets of data as shared array buffers to communicate with, is quite compelling. Also take a look at WitBindgen 1, which is basically a prototype for interface types and supports multiple languages. I agree that interface types/components will be a game changer. And also that progress on all the important proposals, GC, interface types, linking, stack control, threads, has been painfully slow. The whole list of proposals and where they're at is here. You can see that interface types is at a phase 1, feature proposal, CG, so still early days. And there's a link to the proposal here, for people like me who don't know about it. Looking at this, it seems tail calls are still not part of the spec. Has there been any news regarding return_call? Would be cool to see it for more efficient implementation of functional languages. Tail calls are only blocked on a second production engine implementing them. V8 has been done with tail calls for more than 3 years. Is there a good summary anywhere of what's new in 2.0 compared to 1.0? TLDR SAMD new vector types, 128-bit width FP and integer types and values for SAMD with related instructions, and validation thereof, plus memory instructions for wide loads, and support in the runtime for wide values, consts, etc., and in the text and binary formats, value types, I32, I64, F32, F64, are now called number types as new reference types, basically function pointers and pointers to objects in the host, values of which can be stored in tables with related instructions. For accessing them and checking for null, new, table instructions, get, set, size, grow, fill, copy, etc. Element and data segments, not new but expanded definition and given more runtime support, added to the store, can be referenced by address like other runtime objects, plus new indices for referencing segments and their modes, basically, how they are initialized during instantiation, limited form of subtyping allowed when importing external values. Result types can be a sequence of values, i.e., multiple return values from functions. New instructions to avoid trapping on floating. Point to integer conversions, saturation. There's also multiple values. 1. Generalize the result type of blocks and functions to allow for multiple values. In addition, introduce the ability to have block parameters. Function types allow more than one result. Block types can be arbitrary function types. 1. This is exactly what I was looking for, thanks very much. There is some really exciting stuff. I'm particularly excited about stack switching. I still can't find any mentions of external memory mapping without copying it into the heap. Very disappointing as it makes yet another version of WASM completely unusable for many high-performance applications. The multi-memory proposal is your best bet for this. It's supported in WASMtime, WAVM, and WABT and WASM2C, and not much else so far. Are there any improvements in there that would allow for more efficient bytecode interpreters in WASM? As far as I understand, something like E.G, a high-performance JVM would be hard to do in WASM due to its machine's Harvard-like architecture. It appears to include the currently standardized extensions. GC is a proposal in Phase 2, and I'm not even aware or a proposal for DOM access yet, but it would require several other proposals to go through first. As an aside, how does one get involved in the WebAssembly community? For example, if you wanted to get involved in Kubernetes, you'd go to KubeCon, and governance of the OSS project is pretty understandable. What is the equivalent in WebAssembly land? The simplest way to get involved is to start attending the biweekly standardization meetings. The agendas are organized here. To attend the meetings, first join the W3C WebAssembly community group here. Then email the CG chairs at webassembly-cg-chair@chromium.org to ask for an invite. From there you'll get a sense of who folks are so you can pair names with faces when contributing to the various proposal discussions on the many proposal repos listed here. To get a sense of how things are run and decided, read the process documents here. The TLDR is that the community group and its subgroups decide everything by consensus via votes during the meetings. Seek employment at Mozilla, Google, or Apple. Looking for memory shrink instruction. Are there any actual incompatibilities, or is the version number just a marketing gimmick? There isn't a law saying all legit software must use Semver. Python makes breaking changes whenever they want in minor version changes. Technically, even Semver doesn't strictly require you to not update the major version when there haven't been incompatible changes, I swear. A triple negative is the easiest way to parse this sentence. This. The web tries very hard to avoid backwards incompatibilities. I don't expect the WASM standard to ever directly get any backwards incompatibilities, unless they're opt-in, like how using JS modules stops you from using with statements. Only forward incompatibilities, that is, WASM 1.0 engines can't handle 2.0 opcodes etc. Any higher-level developments in WASM land? What about garbage collection? The GC proposal recently moved to Phase 2 and has a lot of momentum. Teams working on compiling Java, Kotlin, and Dart to WASM are closely involved in the standardization effort, and implementations are underway in V8 and other web engines. Right now the bulk of the effort on the standardization side is in tweaking the instruction set to simplify it and improve performance. And on the implementation side the focus is heavily on optimizations, both offline and in the engines. If you want sandboxes, then use Flatpak or force Microsoft and Apple to implement a standards-compliant sandboxing API. The web browser is not the place to do it, and people should be looking at how this will be used to run binary blobs anytime you visit a site. I know folks are excited about WebAssembly, but it's a security nightmare. JS alone is bad enough with most exploits I see that can get you infected just by visiting a page requiring it, even when the issue doesn't lie in JS directly. The idea of letting any random website you visit run code on your machines should give anyone pause, but it seems like everybody is just too excited about the powerful web applications they could make to worry about the malicious web apps that will be created as well. For now I've got WebAssembly disabled, and I don't see that changing. How is the litany of minimized JS used as a compile target, not binary blobs already? There is a difference between obfuscated JS and minimized. Minimized can be unminimized. Also, two wrongs don't make a right.